Hello everyone. In this lecture we are going to learn about stresses in piping components due to temperature.
When we talk of the variable in terms of the diameter, let us take two examples which will stress upon the importance of the diameter from the piping flexibility point of view. So let us take one pipe which is of nominal bore 2 inch, and it is placed on some two supports which are at a distance L. Now, once we are placing that pipe on two supports, naturally the gravity is going to act on it and the pipe is going to sag. So with the next click, you will see how the pipe is going to sag. And this sagging will be some amount, say delta. So the delta will show us what is the amount of sagging, and this will depend on the other physical properties of the piping and its cross section. So then let's take the next example. So next pipe, please. Yeah, next pipe we have say NB 12 inch, and so we place at the same distance. The distance between the two supports is the same again L, and once we place it, it will also sag. Yeah, so next click. Now this sagging will be say amount delta L. So what is the, yeah, so the delta L, if you compare the delta with delta 1, yeah, so we are going to have, so the second one is going to sag less, and we know that the variable which is a diameter of the pipe, so we can say that lesser the diameter, higher is the sagging, higher the diameter, lesser is the sagging. So let's go to the next slide. So here we'll talk of the second variable, which is the thickness. So now we take first case, which is NB 4-inch pipe schedule 40, and we place it at the same distance L between the two supports, and now the pipe will sag by an amount which is equal to say delta. And now the second case, if you take 4-inch schedule 160, that will also sag by an amount delta 1. And again, here we'll have some relation between delta and delta 1, which I think all of you will be able to guess. And we have here delta is going to be, yes, delta 1 is going to be less than delta. And so we can easily say that higher the thickness, lesser is the sagging, because the pipe is going to be strong enough. And if you keep the same distance between the two supports, then definitely we are going to have lesser sagging between the two. So if we can conclude, say higher the diameter, higher is the rigidity of the pipe and lower is the flexibility, and higher the thickness of the pipe, higher is the rigidity and lower is the flexibility. Hope everybody has got this conclusion. So now here we have the next component in the piping is going to be an elbow. So now elbow, what are the properties of the elbow? Bend radius, change in the direction, flow direction or change, short radius and long radius. And when it is higher than 1.5D, what is the terminology that we call? The bends are property wise, they are with different angles. They are 30, 45, 60, etc. But that will not change the basic property, which is the radius of the pipe or radius of the bend. So that is really not going to contribute much to the flexibility or rigidity of the bend. 5D, 6D, yeah, anything more than 1.5D, they are termed as bends. Normally, that is the terminology that is being followed. Miter bends also. Now, miter bends are made up of some pieces of straight pieces of pipes, and they are connected together. Normally, they are not forming part of a critical piping system. They will be used for lower pressure systems and very large diameter gaseous systems or something. So normally they will not form part of a critical piping system. So we will generally skip that part of the bends. Now, okay, so we have all the answers to this. Now, suppose we apply a force to the bend. So we apply force. Now, this force is due to the expansion of the pipe. When we connect the two ends of the pipe to some equipment, and when we pass some hot fluid in it, then the system is going to behave in a different fashion due to the changes in the dimensions of the pipe, for example, the length. And due to that, some forces are going to be generated across the entire length. And once you apply this force, the pipe is going to bend along the bend or the which is connecting the two ends of the pipe. So you can see from the next figure that the shape, which was a perfect 90-degree in the design condition, after applying some forces at both the ends, they change their location. And this is going to be possible only because of the elbow, which is going to be installed between the two bends. So the elbows here, what we can conclude is elbows work as hinges. Then longer the pipe arm lengths connected to the elbows, higher is the flexibility of the piping system. That is very easy to understand because it is nothing but a lever length. So the higher the length of the lever connected to the elbow, the higher is the flexibility of the entire piping system we are talking about. And if you have, for example, if you connect two elbows together, then the system is not going to be that flexible. So the what we want to conclude here is, if you connect one elbow to the other elbow to the third elbow and so on, then the system, if you expect that the system will behave in a very flexible way, so that is not the conclusion that we can make. The elbows must be connected with a good amount of length of the straight piping. Only in that case, they will be able to change the shape, and that will impart some flexibility to the what is the Bourdon effect? Yeah, Bourdon effect is going to be very disastrous for the behavior of the bend. But Bourdon effect normally is not coming into picture for industrial type of piping. It will come only for very high pressure steam piping, where the pressures are of the order of 7500 bar and so on. But for our normal pressure ranges of 5, 10, 15 bar or something, this Bourdon effect will not play much role in the flexibility, because the length is more, so it will act as a lever. It will act as a lever. So higher the length of the lever, the higher the flexibility of the system. So that is the conclusion we can make. And higher is the elbow radius, higher is the flexibility. So as the elbow radius, so we talked about several radii of the bends and elbows. So starting from 1D, 1.5D, 3D, 5D, and so on. So as you increase the bend radius, the higher is the flexibility that you are going to achieve. So and the flexibility of the pipe is why it is very high as compared to the elbow, is because pipe is nothing but an elbow with a radius almost tending to infinity. So that is why it will be having a maximum flexibility possible. If you compare the rigidity of a pipe with respect to elbow, you can safely say that if a connected pipe is say flexibility is 1, then then the flexibility of the elbow is almost 1 divided by 2.5. Or if the rigidity of the pipe is 1, then the rigidity of the elbow connected is 2.5 or higher than 2.5. So that is the amount of rigidity that it imparts, but it will help in achieving the different shape after the forces which are applied at the ends of the piping connections, and that is how it will achieve a flexibility. So elbows are going to help in increasing the overall flexibility of the piping system. Okay, so coming to the next fitting, which is a branch. We saw the piping, we saw the elbow. Now, the next higher number of fittings are branches. Now, we have several branch fittings. For example, let us see the first branch. So, if you puncture a hole in a header and then connect the branch connection and then apply a fillet weld, what is the type of fitting that it is called? It is unreinforced branch connection. So if we talk about a branch connection, the most ancient type of, yeah, set on also they call it. If you the most primitive type of connection is going to be the most crude type of connection, yeah, stub-in connection or unreinforced branch connection. The proper terminology is unreinforced branch connection. There are several other terminologies in use, but the proper definition, technical definition is unreinforced branch connection. That's it. Okay, next click please. Yeah, so the second one where we are seeing something which is welded on it, and then we have some two welds, two annular welds coming up. So what is this type of connection? It is a reinforced branch connection, which is stronger than the previous one, unreinforced, as the name suggests. And then we have the reinforced branch connection, RF pad. Yeah, in short, it is called the RF pad. So this is a butt welding T. So when all the three pipes are connected to the fitting, and the fitting as such is available in the form of a forging or casting in the place, rod fitting. So this is called as a butt welding tee. It comes a ready-made fitting, and then the pipes are butt welded on all the three ends. The connections can be depending on the type of tee, whether it is equal tee or unequal tee. It depends on the branch size, whether it is smaller or same size. This is a weldolet. This is a weldolet connection, and this is almost same as the butt welding tee. So it is also a very strong connection in terms of the strength that it imparts to the fitting at that point, or pipe at that point. And then the last that we are seeing, flexibility, is okay. So this is called a half coupling, which is used for branch connections. And as we know, that if the pipe, the branch pipe, this is a half coupling. So the full coupling is cut into two, and then it is used for branching of small pipes to the main pipe. Now, normally this will not be used in critical piping, or it will not be considered as part of the analysis for critical piping, because this is used for normally for 1.5 inch and less. So we don't go for this type of connections in critical piping. So this is a half coupling connection. So let us come to the some conclusion. Now, all branch connections are very high stress prone connections, because it involves a lot of cutting, welding, fillet weld, butt weld, and so on. So it leads to a lot of stress concentration in that area. And our choice remains only on which type of branch fitting which should use. So stub-in connection is the highest stressed. So the unreinforced branch connection is the highest stress. Then stub-in with RF pad is better than the stub-in connection without RF pad. And lastly, the butt welding tees and weldolets are best and the most preferred ones. So even if sometimes it may so happen that the piping material specification specifies a stub-in connection or RF pad connection, but after the analysis, it may so happen that you have to change that particular location where it is highly stress concentrated to something like butt welding tee or weldolet or something. Okay, so coming to the next fitting in our line. So let us see reducer. So what is this type of reducer? This is concentric reducer. This one is eccentric. Yeah, okay. So eccentric reducer. Now, as far as the flexibility and rigidity of the reducers is concerned, both are equally stressful, and you have not much choice over the selection of this, because the choice of selection of concentric or eccentric will depend. So both the types of reducers are concentrated in that stress, in terms of stress, and we have no choice but to use whatever is required. So they will be accelerating the stresses in the piping system. Okay, so coming to the next fitting, which is the flange connections. So we can see on the left-hand side figure the components of a flange fitting, and on the right-hand side we can see that it is assembled. So flange is a rigid body which will be having a lot of concentrated load or mass on the piping system, and it will be a rigid one. Only thing is the advantage of the flange is going to be it's very small in size. So whatever flanges are there in the system, whether it is slip-on flange or weld neck or lap joint or anything other thing, they will be acting as local heavy bodies concentrated in one location. But the advantage is going to be that they are very small in size in terms of the length along the piping system. So their effect will be felt, but it is going to be very nominal effect in the systems. But what is the disadvantage of this is that if the systems are highly stressed, then you can see on the right hand side, the flange connection may give way. So with heavy stresses passing through the flange connections, it may so happen that eventually if the system is highly stressed, then it may damage the bolt connections. It may damage the gasket which is sandwiched between the two flanges, and it may lead to leakage in the system. So you have to be careful in using this, and while analyzing, you must check this type of requirement for at least for higher pressure ratings in the piping systems. So all these types of walls, they are going to be very heavy in nature. So let us say, so gate wall, globe walls, yes, okay, Y-type globe walls. So all these types of walls, they are going to be big in size. They will occupy some good amount of length along the piping systems, except for these wafer type of walls. All the other types of walls, you see that they are going to occupy a lot of space on the piping system, and they are going to be heavy bodies, and they will be contributing to the rigidity of the piping system. So all in all, we can say that these heavy bodies, apart from the heavy loading, they will have a lot of loading and concentration of the stresses along the in the nearby areas of the piping system where they are located. So all walls and specialties, we will conclude that they are all large in sizes, very heavy bodies, and stress concentration is going to be expected along the pipe. So if a piping system consists of many number of walls, then the system overall is going to be very rigid in nature. These walls are normally considered as 8 times rigid as compared to their connected piping elements. So if a piping element connected to a wall is, say, rigidity is 1 unit, then the wall which is situated on that piping is considered as 8 times rigid than the pipe. So that is how the normally the equation will go. Okay. So coming to the next topic. So let us understand some more facts. Now, let us take case of a piping piece connected to a wall. Now, here in this case, I'm showing only one end connected to the vessel, and a length of pipe L is connected to it. And suppose we apply a temperature to it, then it is going to expand by an amount which is delta L. If the length of the main pipe is L, then the extended part is going to be delta L. And this ratio is called as coefficient of expansion, which is delta L upon L. Now we have a different situation. Now this pipe is no longer free at the other end. In the previous case, we saw that it is free. Now in this case, the pipes are connected. The pipe is connected at both the ends to vessels. And now if we apply a temperature, then the new pipe configuration is going to be that red one, which you can see. The pipe is going to be bent. It is going to generate higher stresses, and because the pipe is not able to expand by that amount in that direction, we are restricting with the help of the equipment. So the equipment are going to experience very heavy amount of forces. So these forces are firstly taken by the nozzle of the equipment, then they will pass through the body of the equipment, and they will then traverse through the supporting legs of the equipment, and then they will reach the structure on which they are sitting. So if it is sitting on the foundation, it will be passed down to the foundation. If it is sitting on a structure, the structure will have to be designed. The foundation has to be designed based on this heavy loading. So whenever we have a piping connection between the two vessels, and if it is not allowed to expand in a direction that is expected due to the temperature that it is going to achieve, and why that temperature is going to be achieved is because the pipe is going to carry some fluid or gas from one end to the other, and that may have some temperature. Now, mainly we are talking about temperature because, as we discussed earlier, pressure in the normal industrial cases are very moderate nature. They will not be that high in magnitude unless you are designing a steam system or something, a 500 megawatt or 1000 megawatt power plant. Only in such cases, the pressures are expected to be high. Otherwise, in normal industrial plants, very few cases will be there where the pressures are going to be high. And in most of the cases, the temperatures are going to be ruling the requirement of the analysis. So let us see, pipe is highly stressed, and at both the ends of the equipment, we are going to experience very heavy forces. Now let us try to find out what is the amount of that force that is likely to be generated. So for that, we will just brush up our knowledge of stress versus strain. Okay, so everybody is aware of this chart, stress versus strain curve, and YS is what? What is YS? Yield strength and ultimate tensile strength. So YS and UTS they will be ruling the requirement of the design of the components. And what is this slope called? Young's modulus. Yeah, modulus of elasticity E, which is equal to, it is also called as Hooke's law. Okay, it is equal to stress upon strain. So if we call stress, denote stress by S and strain by epsilon, then it is the ratio of that stress upon strain is called as the modulus of elasticity, or E, by the, and the equation is called as Hooke's law. Yeah, so epsilon, if you write the strain, it is called as again delta L upon L. So change in length upon the length, which is nothing but our definition of expansion coefficient alpha. Okay. So now internal stress developed due to this strain. If you write that, rewrite that equation, E is equal to S upon epsilon. If you rewrite and take stress on one side, you can say that stress is equal to E into epsilon, or that is the Hooke's law. And if you replace by the above equation epsilon with alpha, we can say that the stress is equal to E into alpha. Okay, next please. Now the force required to compress it back. In the previous slide, we saw that we need a force is generated, and the equal force will be exerted by the equipment on the piping system. Next click, please. So F, if you want to calculate, it is nothing but area of cross section of the pipe into that stress. That is the fundamental equation. So if you replace that stress is equal to E into alpha, the equation will boil down to the force required is force which is required to keep the system in place is equal to A into E into alpha. So where A is the area of cross section of the pipe, E is the modulus of elasticity, F is the compressive force, S is the stress developed, delta L is the actual compression of the pipe, and L is the length of the pipe. So if you follow these units, then you are going to get what is the amount of force required to keep the pipe in place by that amount. So to understand what is the importance of this, let us take one simple example. To evaluate the magnitude of such a force, let us consider carbon steel pipe of 600 mm outside diameter and 10 mm thickness, operating at a temperature of 300 degrees Celsius, and we are restricting the movement of the pipe. So if you try to use the previous equation, so we will get these values from the code. I think many of you would have seen the piping codes. Here I'm quoting from ASME B31.3. You can also refer ASME B31.1. These values do not change. So the value of E from table C6, we get some values which is written there. Then again from the same code and appendix, table C1, you will get the value of expansion coefficient alpha, which is 3.625 into 10 raised to minus 3 millimeters per millimeter. And if you calculate the cross-sectional area of the pipe, the dimensions are given above: 600 mm OD and 10 mm thickness. So our simple formula of cross-sectional area, pi by 4 d4 outside diameter square minus inside diameter square. So inside diameter is now twice the thickness. If you subtract twice the thickness from the OD, you get the inside diameter. So you get these figures. So now we have all these figures A, E, and alpha. So if we multiply all this, so with this equation, we see that the amount of force which is required to keep the system in place will be of the order of 1269 tons, 1269 tons. So that is the amount of force which will be generated if you try to restrict the movement of the pipe at that place. So that shows the importance of the calculation. It is going to generate a heavy amount of force. We have not even gone to the calculation of the stresses in the piping system, which may be really higher than the expected from the code. So this a simple equation tells us that stress analysis calculations are very much important for systems which are carrying fluids with some considerable amount of temperature above the ambient temperature. And if we do not allow for that displacement, then we are going to get tremendous amount of forces on the connected either equipment or support, or even in some cases, maybe even the delicate equipment also, which may not justify and which may not accept this heavy amount of loading on the system. Now, when we saw these tables, we know the criticality of the system. Now, if you have some system in your hand on your table, and if you want to just calculate on your own, just by sitting on your table, you don't have any code in your hand. We have some thumb rules available. So we have some thumb rules. So for carbon steel, the alpha coefficient of expansion is considered as 1.2 millimeters per meter per 100 degrees Celsius rise in temperature. So why rise in temperature? So we are talking about temperature rise from the ambient temperature. So MOC, if the MOC is stainless steel, then the alpha is going to be 1.8. So it is almost 50% higher than the carbon steel. So now if you have any system in your hand, most of the systems will fall into one of the two categories. 95% of the systems will be having either one of these two materials. So you can easily estimate the alpha value. And from that alpha value, once you know the system geometry, you will be easily able to calculate the amount of loads expected on the connected equipment. So let us take one example. If we have carbon steel material at, no, not that one, yeah, carbon steel material at 170 degrees Celsius, and if the ambient temperature is 20 degrees Celsius, what is the value of alpha with respect by the above thumb rules? Let us see. The figure turns out to be a simple equation 1.2. So 1.2, which is the basic coefficient of expansion for carbon steel, which we have taken from the above thumb rule, multiplied by a difference of temperature. 170 is the design temperature, and 20 degrees Celsius is the ambient temperature, divided by 100, because we are talking about every 100 degrees Celsius rise in temperature. So we have to divide by 100. So that equation turns out to be 1.8. Now, 20 degrees Celsius temperature, ambient temperature may vary with region to region. Suppose you are in India, 20 degrees Celsius ambient temperature is good enough. Suppose you are in Gulf, what do you expect? 33. Okay, you are operating at 33. MOC stands for material of construction. Yeah, here you can see the alpha is 3.625 from the code. So now here the material is carbon steel, you can see, and temperature is 300. Do you find that we are almost nearby? You will find that our thumb rule will take you to this figure without going into the code. The alpha value which we have taken from the code is 3.625. Yeah. So, and our thumb rule says that we have 1.2 as the basis. Yeah, right. Almost 1.2 into 3. Just that 20 degrees Celsius subtract from the 300, which is a minor figure. So we are almost there only. Okay. So next slide, please, and we'll go to the. So that tells us the importance of understanding this thumb rules for the alpha, and sitting on your table without going into any other place, finding out the alpha, you can easily guess what is the amount of load expected for your system on the connected thing, and then you can decide whether you want to really go for an analysis or not. So that is the basis of this. Okay, so in this entire course, we are going to see the basic theory for the stresses which are going to be generated because of this, understanding the expansion, the strain, the
Launching
expansion
of
loads,
online live
then
sessions
what are the
on
types of
pipe stress
different
analysis and
loads
Caesar,
other than the
2 course.
expansion, like occasional loads, which are going to be affecting the entire analysis of the piping system. And then we will see what are the theories of stresses which are defined by the code. And then we will also understand what are the different types of stresses which we have to adhere to, and make it acceptable to the code, which are not generally not seen as part of the other components. For coming to the piping, it is a particular different type of stresses which are going to be seen, and then the code asks us to calculate that amount of stress, and then it allows us to limit it to some values. So we will understand from that theory how to calculate those stresses and limit those different types of stresses to the values given by the code. Then we are going to see the code requirements, the piping code references, the code compliances. What does the code say about the requirements of meeting the stresses, highest stresses values? Then we will study the theories of failure. We will also understand the complex stresses in terms of the secondary stresses which are generated due to temperature, and the concept of the stress intensification factor, which is going to be a more important from the point of view of the analysis and how it affects the entire analysis. Next slide, please. Then we will also study what are the different solutions. So once we understand what are the problems which are there in the system from generation of or passing of the temperature, then finding out the problems and then attacking those problems to resolve and meet the code requirements. So we apply different techniques like enhancing flexibility, adding the expansion loops, then play with the friction along the pipe supports, use of springs, bellows, etc. So the and then understanding the equipments. So static and rotary equipment, they have to take the loads from the critical piping system when we analyze, and they also play an important role in meeting the requirements of the code, because the stress analysis, once it is done, it's not only that the piping will be required to be meeting the requirements, but the connected equipment, the connected structure also needs to be satisfying and meeting the requirements of the entire system, so that the entire system remains safe. It is not only piping which needs to be safe, the connected equipment, the connected supports on which the piping is resting, that also needs to be safe. And the code places the onus on the stress analyst for this purpose. Then we are going to see the other types of loadings, which are in the form of wind, seismic, the PSV reactions, and there are some more reactions also like snow, blast, etc., which will be there, and we will just study those reactions in the piping systems. Then we will see the entire understanding of the supports. So what is the requirement of the supports from the point of view of code? Then various types of supports from the construction, various supports, how to take the supports from the equipment, the functional types of supports, which are in the form of resting, guide, axial stop, anchor, fixed point, etc. Then use of spring supports, which are other than those rigid. So far, we talked about rigid supports. Now, these are the flexible supports like spring supports, and then understanding what are the different types of spring supports and selection of the springs from the vendor catalog, which is an important part. Although the code, the software also finds out, but then we must know and we must be able to play with the selection of the springs from our understanding of the vendors' offers that we have. Then we'll study the entire Caesar 2 software, that is in the form of what is the data collection which is required for Caesar, then overall the views, overall functions which are provided by the Caesar 2, and then we'll go from the basic modeling requirements, then piping modeling, equipment modeling, the built-in database which is available, restraint modeling, and then we will add one by one as the cases are there, the seismic requirements, the wind requirements, PSV forces. If there are some initial displacement from the connected equipment, that also will be done. Then we will study what is the how to calculate a loop on a pipe rack, and different types of loops, 4D, 4 band, 6 band, etc. And then we will continue with detailed problem solving with the help of what are the different facilities available in the Caesar for ease of modeling. And then we'll apply the technique to find out various systems which are subjected to a temperature pressure variation. Many systems will operate in such a way that in one cycle they will some part of the piping is going to be hot, another part is going to be cold. After some time, the previous part which is hot will be cold, and the earlier which was cold, which is going to be hot. So how to analyze such systems, and such cases may be 2, 3, 4 different types of operating conditions will be there. So here we need to understand how the operation of the entire system is going to be there, and we must apply all those operational requirements to the system, so that we will understand the analysis of each of operation. Then in this particular thing, we are also adding some super advanced requirements such as modeling of the spring supports, modeling of the bellows, then flange failure checks. We were talking earlier about flange when sometimes if the stresses are very high, then the flanges may also fail. So how to check the flange, this thing. Then initial displacements, how to impart initial displacements, how to impart nozzle flexibility, because equipment is having a nozzle, and that nozzle is also having some flexibility. So how to take advantage of flexibility of the nozzles which are mounted on the equipment. Then how to check the nozzle loading limit checks supporting from the equipment, and some dynamic understanding of the analysis like natural frequency calculation, slug and plug possibility, two-phase flow. And then piping subjected to dynamic seismic response spectrum method. So all these very high super advanced courses which are normally not included in other courses which are available in the market, that also we are going to cover in this particular session. So it is going to be really a useful tool for everybody, and it's going to be a giant jump in the form of your career in your life.
Now, let me just tell you more about the course. So this syllabus has been already been discussed. We are going to cover a content which is from basic to super advanced level, theory, examples, and we are also going to cover software part, that is Caesar 2. So these are going to be online live sessions. The way we are conducting this webinar, this is live. Similarly, these are going to be online live sessions. Whatever syllabus has been discussed by Sudhir sir, to cover those syllabus, it will take around 55 to 60 hours. That will be spread in 5 to 6 months. The first class we are going to start on 3rd June, and the timing is going to be the same, 8:30 p.m. and we are going to fix the weekdays, Tuesdays and Thursdays. So this classes will happen on every Tuesday, every Thursday, sharp at 8:30 p.m. Each session will be of 1 or 1.5 hours. And as I was saying, there is total content of 60 hours, which is spread in 5 to 6 months. Upon the live sessions, you will also get a recording, because we also understand that since it is on a Tuesdays and Thursday, there might be a chance that you might miss out a couple of lectures. So to help you out, so that you cope up with the online sessions, the recordings will be shared with you. You can go through the recordings, you can use the recordings. If you have missed out anything, you can use the recordings for the revision purpose. But the recordings of each and every session will be shared on our learning platform. And this, on the learning platform, you will also have test. There will be material which will be available. And the access to the e-learning will remain for another 1 year after the course is completed. So that means for the 5 to 6 months, you will already have a access to the e-learning platform. But even after the course completion for another 1 year, the e-learning access will be available for you for the revision purpose. And very important, you will also have a support of Q&A sessions. So when we are having a live session, of course, during the session also you will have a Q&A session. But even after completing your course after 5 to 6 months, you will have another support of Q&A session for another 1 year. And as we do it for the static courses, here also there is a WhatsApp community which will be available for the discussion purpose. So after the course completion, depending on the performance of your test, a certificate will be issued to you, which will have a grading system.
To learn more about the piping course, fill out the Learn More form in the description below.